When people say HTTPS, they usually mean encryption. But encryption is only one piece. Today, we will unpack what TLS really does, so you understand the handshake, certificates, and why your browser trusts a site in the first place. Here is the myth in one line. HTTPS equals a secret tunnel. The reality is broader. TLS is designed to give you 3 guarantees, because a secret tunnel to the wrong computer is still a disaster. TLS solves 3 distinct problems. Confidentiality means nobody on the network can read your data. Integrity means nobody can quietly change it in transit. Authentication means you are talking to the real server, not an imposter who happens to speak encryption. Picture online banking. Without confidentiality, someone reads your password. Without integrity, someone changes the transfer amount. Without authentication, you might be typing your password into a fake bank site that looks real, perfect encryption, wrong owner. To see how TLS sets up a secure session, you need 2 building blocks: symmetric crypto and asymmetric crypto. HTTPS uses both on purpose. Symmetric encryption, think AES, is fast. Both sides share the same secret key and use it to encrypt lots of data. That speed is why the web uses symmetric crypto for the heavy lifting after the connection starts. But symmetric crypto has a chicken and egg problem. How do 2 strangers agree on a shared secret over the internet before they have any secure channel? You cannot just paste the key in plain text. Anyone watching would copy it. Asymmetric encryption, like RSA in older setups, uses a public key and a private key. Anyone can encrypt with the public key, only the owner decrypts with the private key. It is much slower, so the web typically uses it only to bootstrap the session, not to encrypt every page forever. Put it together, and you get a hybrid design: asymmetric style key agreement plus symmetric bulk encryption. That is the practical balance browsers and servers use every day. Modern TLS 1.3, does the first flight of the handshake in about 1 round trip. That means the browser sends a bundle, the server answers with a bundle, and both sides can start deriving keys quickly. Think of it as a tight exchange, not endless back and forth chatter, just enough messages for both sides to pick algorithms, exchange key material, and validate identity. Faster handshakes mean snappier page loads and happier users. The ClientHello is the browser introducing itself. It offers supported cipher suites, sends randomness for freshness, and includes a key share, public material that will be used in the Diffie Hellman style exchange we will visualize in a moment. The ServerHello picks the cipher, adds its own randomness, sends its key share, and presents a certificate chain. That certificate is how authentication enters the story, the cryptographic ID card for the website. If you zoom out, the transcript looks like this skeleton, not every byte, but the idea. Hello's establish parameters and key shares. The certificate carries the server's public identity key for verification. Diffie-Hellman key exchange is often taught with a color mixing analogy. Imagine a public base paint everyone sees. Each side mixes in a secret color only they know. They exchange the mixed results, not the secrets, and both can derive the same final mixture without ever revealing their private colors to a passive observer. The public mixes are safe to send because reversing the private ingredient is meant to be hard, like unmixing paint in the story. In real TLS, the math is discrete logarithms or elliptic curves, not paint, but the pattern matches. Publish key shares, keep secrets private, compute the same session key. The attacker on the wire might record everything public. Under the right assumptions, they still should not be able to recover the shared session key. That is why key agreement is powerful. You get forward secrecy when keys are ephemeral, more on that shortly. Key agreement protects confidentiality and integrity for the session, but authentication is a people and process problem too. Certificates connect a domain name to a public key, signed by authorities your browser already trusts. Your operating system and browser ship with trusted root certificate authorities. A site certificate is typically signed by an intermediate CA, which is signed closer to a root. Your browser walks the chain, checks signatures and validity dates, and ensures the name matches the site you intended. In X.509 format, think of a certificate as a structured document. Who it is for, who issued it when it expires, and the public key you use to verify signatures and help set up encryption. A self-signed certificate still has a public key, but nobody independent attests the mapping from name to key. Your browser warns because authentication failed the chain of trust test, even though traffic might still be encrypted. Encryption without verification is a classic pitfall. Forward secrecy is a headline feature in TLS 1.3 style deployments. The idea is simple and powerful. Compromise tomorrow should not decrypt yesterday. TLS 1.3 pushes ephemeral key shares for key agreement. That means the long-term server identity key is not the same thing as every session's symmetric secrets. Each session mints fresh key material, limiting the blast radius if something leaks. If someone steals the server's private key later, forward secrecy aims to keep old captured ciphertext useless. They would need the ephemeral secrets from each session, which were not kept around. That is the intuition. Operational hygiene still matters in the real world. So HTTPS is not a single switch labeled encryption. It is confidentiality, integrity, and authentication, implemented with hybrid cryptography, a fast modern handshake, certificate chains you can reason about, and forward secrecy to protect the past. If this clicked, subscribe for more plain English security breakdowns.